start this here. Okay. All right. I guess I should have closed the door. So no classes this Friday means that there's no lab, so that might be nice. Let me just close this door. And the back door, I guess. And I should have waited to start the recording. All right, just check back in here. So unfortunately, I won't be able to see, or if you put anything in the chat now, I won't be able to see it. So if you need me to know something, you'll need to speak up. All right. I have a note here. Did I tell you guys to check out spurious correlations last term? If you go to spurious correlations, it has all these things that are highly correlated with each other, even though there's no relationship, right? So US spending on science, space, and technology correlates with suicides by hanging, strangulation, and suffocation. So obviously those don't have anything to do with each other. The number of people who drown by falling into a pool correlates with the number of films that Nicolas Cage appeared in. So kind of weird. They're all pretty morbid, but it is kind of fun to look at. So, wait, wrong screen here. Just for fun. Check out spurious correlations. Wait. I guess it's actually at tylervision.com, but just for random things that are correlated but not related, obviously. I can't remember what we did last week. It feels like so long ago. Oh yeah, we finished classification, and today we're going to start chapter 6, which is the last chapter that we have before test 2. And so today we start chapter 6. And just as a reminder, test number 2 is on chapters 4, 5, and 6, I want to say. Yeah. Okay. Let me see if I can see when that test is. Test number 2. November 22nd. So we do take our time kind of working through chapter 6. Today, I'm only going to do K-nearest neighbors, which is probably something you've seen before, but it doesn't hurt to see it again. I feel like every time you see something again, you'll learn something, or at least become more familiar with it. And so test number 2 is on November 22nd. And I'm gonna check the chat just in case, even though I said I can't see it. I just felt like sometimes people throw stuff in there anyways. Chapter 6 is called Statistical Machine Learning. Now, I know that you take at least one course on machine learning, if not two. Okay. And so here, of course, this is just one chapter in among 7, so we're just basically scratching the surface. Right, you'll see more with, is it Bevan who's teaching that one, or is it Bevan and Julian? Can't remember. I ask you questions even though I tell you I can't see the chat. Anyways. So you will see more obviously in the course called machine learning, but this is a nice place to start. And what I find is, especially because the code gives you all these little code tidbits, then that might be helpful. Okay, so today we're going to do k-nearest neighbors. KNN for short. Okay. There are 2 ways that we can use k-nearest neighbors in kind of 2 capacities. We can use it as a way to make predictions, right, or classifications, depending on what the outcome is, or we can use it as a feature engine. Okay, so we can use k-nearest neighbors in 2 capacities. The first one for classification or prediction. Classification is the term we use when we have a categorical outcome. Whereas prediction is the term we use if we have a numerical outcome. Predicting the outcome. The second option is as a feature engine, which really just means, and I should clean that up here, we can use it to develop predictor variables. So what we do is use the values from the classification or the prediction, depending on what outcome it is you're looking at. So use the classification or the prediction from 1, right? So up here, where that's the end of the road, but now what we can do, instead of just ending there, now I can use this new thing as a predictor in our classification model or the prediction model, right? And so in our classification model, for example, maybe logistic regression is the most common one that we use now, or prediction model, right? Maybe linear regression. Something like that. Okay. Now the term feature engine just means you're developing a predictor, right? And so just recall here that an explanatory variable is the predictor, or are the predictors, which are the features, right? So by saying a feature engine, then what we're saying is I'm just creating new predictors or new features. Yeah. So what we do is, in terms of the k-nearest neighbors, our goal is, given a set of predictors, we want to classify or predict the outcome. Classify or predict the outcome. K-nearest neighbors, you may remember, is it looks for the values that are closest to the thing that we want to make a prediction for. And so first thing we do is we search the data set. We search the data set for the observations. No, we don't actually search it, but we search it for the observations in theory with predictor values closest to the predictor values of interest. With predictor values closest to the predictor values of interest. Now, this term closest is going to be really important, right? Because how do we measure closeness, right? How do we measure distance? And so we've got a couple of options. And then the second thing that we do, so we search the data set for those neighbors, and then we look at those neighbors and we can consider the majority, right? Or we can consider the average outcome. Right? There are lots of different things that we could look at of those three nearest neighbors, for example, right? But the second step is the actual classification. The majority determines the classification. Whereas if I'm talking about a prediction, right, so a numerical prediction, then the mean might be, the mean outcome will be the predicted outcome. The predicted outcome. Oops. Yeah. So here, the majority or the mean, right? We could talk about other methods, right? The majority means that more than 50%, that's a decent cutoff, right? But let's just say other methods exists. Other methods exist, but these are the most popular. So if you're stumped, it's nice to have a good jumping off point, popular there. Okay, so for classification, then you're going to look at the majority, right? And so, for example, if you have 60 out of 75 were class 1, right? then the class is going to be equal to 1, right? Because the majority were class 1. In terms of the other methods, right? So the majority, it's easy to wrap our head around. The mean, it's easy to wrap our head around. Oh, well, because this was the average of the 3 closest outcomes, this is what I predict it's going to be. That's easy to explain, right? If you're using other methods that are not as easy to explain, right, then you still have to explain it to your boss or your client, right? And so just keep that in mind, right? And so in terms of that other methods exist, right? Remember, you will likely need to explain your choice to a client. Okay. So the majority or the mean are going to be the easiest to explain. Remember, you will likely need to explain your choice to a client, and the majority / the mean, depending on the scenario, is the easiest to explain. So unless those other methods that you're looking at give you significantly better results, right, then maybe it's worth explaining to your client. But if it doesn't, then it's not worth it. So we said earlier that we find the closest predictor values. And so we need some way to measure closeness, right, or distance. So KNN considers the K closest neighbors. Which means we need to measure distance. Now you might remember the distance measures from, well, we definitely talked about it in data 300, right? But that was probably a long time ago. So we'll need some distance metric. Okay, so closest or distance is measured by a distance metric. A distance metric. And the default is going to be the Euclidean distance. And the default is the Euclidean distance. Okay. The Euclidean distance from point A to point B, let's say, is going to be this distance. And maybe this is the Euclidean distance. And you might remember A, B, C is the Euclidean distance, and Pythagorean theorem says a squared plus b squared is going to be c squared, which means that c is equal to the square root. Sure. of a squared plus b squared. We're going to have more than just two predictors in our model, right? So in general, we're going to have the Euclidean distance Oh. Did you have a question?
Nope.
No. Okay. I just heard rustling I hadn't heard before. Okay. So the Euclidean distance is going to be x1 minus u1 squared, where x is going to be the sample observation and u is the predictor value of interest. So I can still go ahead and find the distance between x2 and u2 squared plus all the way up to as many predictors as I have, xp minus up squared. There. The Euclidean distance is the default, so it is going to be what we're going to be using. But we could also talk about the Manhattan distance. It's kind of the easiest one to wrap our head around. So we could also consider the Manhattan distance. Which between A and B is going to be, the Manhattan distance is going to be from A to B. Or if you prefer, right, you could go up first and then over. They're going to be the same. The key is that you can only move in one direction at a time, right? So either you move left or right or up or down. One thing to keep in mind with this, thought I was in pointer mode. With this Euclidean distance is that the scale of these predictors and the observations, obviously the predictors and the observations are going to be on the same scale, but if I take this square root here, copy. When we find the Euclidean distance, the scale of x, the x's and the u's is going to affect the distance. When finding the Euclidean distance, the scale of the predictors can greatly affect the distance. So for example, if I paste in that distance, right? If we think about maybe a real estate data set, right? If this predictor one or observation or yeah, it is though, but predictor one, right? Maybe this is predictor 1 is the number of beds, right? Let's say it's on a scale of 0 to 5, right? Maybe, right? Maximum we have is 5 bedrooms. Okay. Whereas let's say this is predictor 2 is the number of square feet in the house. It's the square footage. Okay. Then let's say the scale for predictor number 2 is between, let's say, 600 square feet to 3,000 square feet, right? So these scales from 0 to 5 and 600 to 3,000, right? That's going to affect the distance. So when we try to minimize the distance, right, the square footage is going to be constantly overpowering our calculations, right, the distance calculation. Yeah, and so when we try to minimize the distance, we end up only considering the square footage because it's on a large scale. Square footage because it is on a large scale. So obviously, to avoid this, one of the things that we could do is we could standardize all the predictors, which really just means calculate the z-scores for all the observations. To avoid this, maybe I'll do this. So to avoid this, we need to standardize the predictors. Which really, what I'm saying is we need to calculate z-scores for all the observations of all predictors. Z, remember, is x minus x bar over s, which is really going to tell me, okay, if I take this observed value and I subtract the mean and I divide by the standard deviation, it tells me how far this x is from the mean. So this is finding the distance x is from the mean. And the distance in this case is the number of standard deviations. One thing that I don't seem to have in my notes, and I guess it's pretty obvious, but when I'm doing these calculations, right, I need to have only numerical values in here. That doesn't mean I can't include categorical data. As long as I'm able to transform them into numerical variables, then that's okay. Or even one hot encoding we can use, right? But because I'm calculating the distances, I need to only have numeric predictors. So here, in order to be able to calculate distance, we need all the predictors to be numeric. We need all the predictors to be numeric. Okay. Not numerical variables, just numeric. Okay. And so one of the most common things that we do, well, that doesn't mean I can't have categorical variables. Okay. So what this means is, we will need to transform categorical variables into one-hot encoders is what we use. This means we will need to I don't want to say transform, convert. Means we will need to convert categorical predictors into one-hot encoders. One-hot encoders is different from in regression where we used, we left out one of the categories. We did use one-hot encoding, the kind of creating a dummy variable, but one-hot encoders means that we're going to keep all of the categories and we're going to have dummy variables for all of them. So that's the difference. One-hot encoders is that each category is recoded as a binary variable. One thing here is that unlike regression, all are kept. Okay, and we include all of the categories in our nearest neighbor's distance calculation. So therefore, all categories must be part of the distance calculation. And that's how I remember that, okay, for k-nearest neighbors, I'm looking at the distance, right? I'm not predicting using these dummy variables, and then I'm worried about multicollinearity anymore. Right now, I'm just looking at the distance. So all categories must be part of the distance calculation. Okay. So that's a main difference. Right. Okay. So in terms of the number of neighbors that we're going to consider, we have a range of options kind of between 1 and n, right? So k is the number of neighbors we consider. Right, and so we have a few options. We can start at k equals 1, which is going to mean what? That's only look at nearest neighbor, nothing else, right? Whatever your closest neighbor is, that's what the predicted value would be, or the predicted classification is. And then we can, on the other extreme, if I use n, which is my sample size, right? If I use the entire sample as my nearest neighbors, then what's going to happen? All those predictions or the classifications are the same. If you consider the entire sample size, right, every single time, you're going to get the exact same prediction, right? So that's not very useful either. All predictions or classifications are the same. And that is one of the options. It's just not very efficient. Are the same if we consider the sample size nearest neighbors. So what we want is we want to find something kind of in between here. We want to use a K that captures distinguishing information. So what that means is, okay, well, looking at just one nearest neighbor isn't that helpful. Considering the entire data set is also not that helpful, right? And so we want to find a K that kind of does it all. So we want to use a K that captures distinguishing information. Usually we're going to consider a K between 3 and 5. Three, 4, or 5, right? We can do more, we can do less, but depending on, your sample size and that kind of thing, then 3 or 4 or even 5 is good. Okay. So, okay, let's see here. I feel like there was something I wanted to add in here, but so once we've decided what our K should be, and we are able to find our nearest neighbors, and I do want to use the code from the textbook just to walk you through that code. But when we say, so this is how we would find the prediction or the classification, but what if we want to use it as a feature engine? And so to use K nearest neighbors as a feature engine, oops. In a classification or prediction model, right, then you've got y hat is going to be beta 0 plus beta 1 x1. This is the theoretical model, beta 2 x2 plus beta 3 x3. And this x3 could be the K nearest neighbor prediction. What if I put that up here instead? Can I put this all on the same page? Wait. There. So then here, right, I would incorporate that prediction which does what? It's based off of X1 and X2, for example, in this case, right? But it incorporates only the 3 nearest neighbors or the 4 nearest neighbors, so not all of it, right? And so that's how we're able to avoid the multicollinearity aspect, is because it's only considering the nearest neighbors, not all of them. Right? So a couple of things when I was playing around with resume. Of course, it doesn't like it when I go and leave it for too long. When I was playing around with the code from the textbook, right, there are a couple of things. And so what I'm expecting that you're doing is you get this code, right? And of course the lab questions basically just get you to use this code. But once you have this code, clean it up and just make sure that it's running just the way it is, right? If it's not, you might need to fix something. So let's see here. Oh, turns out it's very difficult. Oh my gosh. I just want to run this. Oh, sorry, I didn't realize I hit it so many times. So run the libraries, that's fine. Looks like I've done it a bunch. And then read in the data sets. Now, I've obviously changed this so that I can just have the loan data in my working directory, and then I can just access it. But make sure you use the strings as factors equals true in there, right? And then they also do some manipulations in the data set that they don't show in the actual print of the textbook. And so just make sure that you do all that part. Going to bring in this data set or these data sets. There they are. I haven't run the XGBoost command yet, so I don't know. So I commented that out. So what we're going to do is from the loan 200 data, we want to predict the outcome of the first row. Okay, so if I look at the head of the loan, right, notice that the first outcome is empty, right? But I've got a payment income ratio of 9 and a DTI, which is what, the debt to income ratio, 22.5. Okay, and so this example, what we want to do is we want to keep this on the same page here. There. Try to stretch this out. Okay. And so here, this example, what it does is we want to predict in this example, oops, we predict the outcome, the first outcome. Okay. So there were a couple of things that they went through and did, right? And so, for example, the new loan is going to be the one that we're predicting. It's the first row and the two and the second and the third column. The drop equals false. I found a link that might be helpful, which you don't have, but how can I do that? I just searched for drop equals false to see. These are notes to myself, right? And so I've manipulated this code. So like I added the head as the loan of 200, for example. I changed how I import the data up here, All right. And so now I'm ready to just work through and just see how this all works. Okay. So my next thing that I ran it into was uh oh yeah, first thing I was wondering about was the drop equals false. I guess the problem, right? If I just copy this, is that it doesn't, so R doesn't keep um R does not keep, and how do I copy this? Okay, I guess I'll just run it. So now it's one observation of two variables, which is what we wanted, right? Whereas if I change this just temporarily to say drop equals true, which is going to be the default, and then I run that. Okay, notice how new loan now. Oops. Wait, this is harder than I thought to do it on my iPad. Anyways, new loan is now a list of two, which is not what I wanted. I didn't want it to be a list of two. I still want it to be just a miniature version of the data set, right, where it maintains those columns. And so the drop equals false does that. So now I have one observation of two variables, whereas before it was a list, right? So the drop equals false is what does that. Uh-oh, I accidentally refreshed. Okay. So then, so as I'm reading each line of code, right, you want to be really careful that you really understand the arguments that it's giving, right? And so for each thing that I'm not 100% sure on, I just look it up and I add a little comment to myself, right? Drop false is explained at this link, right? But now I know what it is, so I don't need to worry about that anymore. What if I run the KNN function? Okay, it needs a training set, it needs a test set, so that's all fine to me, right? The training set is going to be the entire Loan 200 data set minus the first row because I don't want to use the one that I'm trying to predict it, right? Kind of makes sense. And then I want to test it with the new loan. The one thing that I kind of got hung up on was the CL. So let's just run this code. And then, right, I had a hard time with the CL. It wasn't obvious to me what it does. And so if I run question mark, KNN, it comes up with the class KNN. So you choose the one that's appropriate. Okay. And here, the CL is a factor of true classifications of the training set. So save. So here, the factor of true classifications of the training set are -1 and 1. So it's the Loan 200 without the first row, and it's the first column. Okay, so here, right, if I'm trying to figure out what this is doing, right? This says from loan 200, subtract the first row, or maybe not subtract, remove the first row. And the first column is are the true classifications of the training set. Are the factors of the true classifications of the training set. Okay. So I'm not just running the code, I'm completely pulling it apart. The k equals 20 seems obvious to me, the 20 nearest neighbors. And then, so once I have it stored in KNN pred, then I can see, and this is going to be a logical expression, a true false, right? KNN pred, does it equal paid off? Once I go here, right, KNN pred, oops. If I wanted to look at it, right, it gives the index of the nearest neighbor as well as the distance, right? So of course you're going to go through and you're going to find the smallest distance. So a distance of looking at, well, I don't have a pointer on here, but the first distance at 1, 1 is 0.4378799, which is the 35th away from the first observation, right? A distance of 0.88, we would expect it to be further away. And in fact, it's at 182, right? And then, so now I can see if it's paid off, and that's going to be true. Okay. So what we can do is we can figure out just based on the index, okay, of the, wait, I can find the nearest points. Okay, so there, if I hit these nearest points, right, it's going to be observation 36, observation 183, 182, and it has all those payment income ratios. These are the closest, as also considering the DTI. We haven't standardized, right? So that could make a difference. Oh yeah. So here's just a few those nearest points again. And then I can store the distances. Yeah. Then they make the circle function, which really just creates a circle. So I'm going to ignore that. It's not part of our analyses. It's just part of visualizing. Okay. This is where I kind of get a little bit lazy, because what I want is I want to look at that image. Okay. But you're going to go through each line of code and just make sure that you know exactly everything that's going on. So then I'm gonna finally create this graph. So X is where the new loan is. That's a payment income ratio of 9, I think. Yeah, 9, and a DTI of 22.5. And then we're able to find, so notice how we've got it nice and easy because we only have 2 predictor variables. The idea stays the same, but it's a lot harder to visualize with more than two variables. Okay. So here, the idea is easy to visualize with only two predictors. But the same idea goes for more than two predictors. But the same idea applies to more than two predictors. Okay. So, of course, I didn't do all of it, right? The next thing we're going to do is to normalize with the z-scores, but I want you to just poke around. Even though we don't have a lab this week, it doesn't hurt to poke around with this, with the code that you have. And I think that's good for today. All right, I'm going to stop this recording. See you on Tuesday or Thursday.